Hello, good afternoon. Buenas tardes. Magandang hapon. I'm Dan Matus. This is N.A.V.I, Anthony Ortiz, Justin Mateo, Bruce Lee, and Victor Nguyen. We are Team N.A.V.I. We are sponsored by San Diego State University, and our project is Micro Mouse. Micro Mouse is an IEEE competition held every year where entrants are required to build a fully autonomous mouse that is no larger than 25 by 25 centimeters in length and width, and may not exceed a $500 price limit. This mouse is then required to solve a 16 by 16 unit square maze within 10 minutes, where it's not allowed to leave parts of itself behind, touch the walls, or break through the walls. This is the basic functionality of our mouse. We have a microcontroller, sensors, stepper motors, and drivers, and our batteries. And in our block diagram, you can see that our IR sensors send signals to our microcontroller, and our microcontroller sends signals out to our drivers, to the stepper motors, all powered by our battery. And we also have a UI consisting of L and N.A.V.I. Now here's Lenny Chan to flood and fill your mind.
So the algorithm we chose to solve the maze is the flood fill algorithm, and the reason we chose that is because it finds the shortest path. To implement the algorithm, you would first assume that there are no walls in the maze, and you assign each cell a distance value to the center. And when moving the mouse, you would prioritize moving to the cell with a lower distance value. And I have an example here. In the first picture, you can see that the mouse started in the lower left corner, and it moved north one cell. Now it scans for walls. It doesn't find a wall to the north or east, so it can move either way. But since it is moving north already, it would prioritize moving north, as you can see that it has in the second picture. And it scans for walls again, and it sees that there is a wall to the east. Now it updates the distance value, and as shown in picture 3, and the last picture shows the fully mapped out maze and updated values. And here's a video of our simulation. We have two modes for our mouse, mapping mode and solving mode. This is the mapping mode. You can see that as it moves throughout the maze, it draws out all the walls, and it updates its distance values along the way. Once it hits the center, it goes backwards, and it cuts off all the dead ends and invisible cells, so that sets it up for its speed run solving mode.
Anthony Ortiz, tell them how we see.
So for our mouse to see the maze, we got these sharp infrared sensors which detect distances from 2 centimeters up to 15 centimeters. And as you can see from the diagram, one half of the sensor emits an infrared beam that then reflects off the walls and then is received by the other side and outputs an analog voltage that's inversely proportional to the distance received. So we're going to have 3 of these on our mouse, one on the front, the left, and the right. So we tested these sensors by applying a 5 volts across the sensor and then received an output voltage. So over there you can see that as the wall comes closer to the sensor, the voltage rises, and as it goes away, the voltage decreases. So while testing these sensors, we found that there was additional noise across the sensors. So we actually added a capacitor to reduce that noise and get a clear signal. While implementing it for our actual mouse, we used the onboard analog to digital converter with direct memory accessing, and we set the microcontroller to the resolution size of 12 bits and set it to continuous scan mode. So in this scan mode, it continuously grabs the voltages from the sensors and then converts them into ADC values, which can be computed with this equation here. It then takes those values and then stores them into a value array, which we use that array in order to move our mouse through the maze.
Justin Mateo, tell them how we go.
Stepper motors, bro. So we're using the N.A.V.I 14 bipolar stepper motors, but you guys must be wondering, what is a stepper motor? Simply put, it is a motor that utilizes a magnet that spins in the center and is surrounded by coils. And the coils alternatively turn on and off, attracting the magnet, causing it to rotate, as you can see in the picture. And the unique thing about this is that each rotation, or step, measures about 1.8 degrees. And that means that our motor can achieve 200 steps per revolution. And this is important for our mouse because as it moves through the maze, we wanted to know where it is as it goes through the maze. And it is much larger and slower compared to DC motors, but we decided to go with precision over speed. But in order to move our motors, we need a separate motor driver. And we chose the DRP-825 separate motor driver. And this driver gave us the option of using micro-stepping mode. We are using the 16 micro-stepping mode, which requires us to have more steps per revolution. And it cleans up the rotations as well as being more precise in its steps as it moves through the main. Now, in order for us to know where the mouse is within the maze, we need to count how many pulses it takes to go from the center of one cell to the next cell. And we calculated this to be about 2,300 pulses to go from the center of one cell to the next. And for our turns, approximately 1,700 pulses for our turns. And for our U-turns, just double that value. And these numbers basically reflect the customized wheel that we created for our mouse. And it was about so many millimeters in diameter and 20 millimeters in circumference.
With all these values and data, we have our microcontroller that has the analog digital converter. So we've taken the values from the higher sensors to determine whether the walls to the left, to the right, or in front of our mouse. And we also implemented other pins to monitor our battery. And the microcontroller also sends out the pulses to our motor drivers to make the mouse move and whether we're going to turn left or turn right. We first had going through the maze, we had our prototype chassis, our white chassis, but the weight wasn't evenly distributed, so we were pumping wheelies all day. Then our second was our black chassis, but it was just too big for an 18 by 18 cell. So we designed our final chassis to be more compact. So we cut wheel wells, so then our wheel would be tucked in, rounded out the edges, so when we turned, we wouldn't be hitting walls. And even a battery trunk, so that we could store our battery without it being sticking out. So our final mouse became small and compact. We were no bigger than 10.5 centimeters by 10.5 centimeters in length and width. We had minimal wiring thanks to our PCB. We also implemented our on and off switches and switches for our modes, our mapping and our solving. And we even had LEDs to indicate whether we were turning left, right, or making a U-turn. Now, Bruce Lee, talk to them about money.
So our project, we had a $600 budget, and we spent a total of $520. And the majority of our money was spent on hardware parts, microcontrollers, sensors, and stepper motors. And these values not only also represents the spare parts that we bought, as well as experimental parts that didn't meet our specifications. Our total remaining is $71.95. And as Daniel explained earlier, the IEEE regulation stated that we can't use $500 worth of parts on our final mouse. And before we started this project, we projected that we would use around $200, but the actual amount used was $196, which comes to prove that we're pretty good at projecting things.
Project with, project your voice.
Okay. So in our milestones, we have 3 stages. The first stage is the planning stage. This stage is where we research about the mouse, see what kind of motors we want to use, see what kind of wheels we want to use. Once we have everything figured out, we go to the second stage, which is the building, the coding, and the testing stage. Those include the motor control, the chassis design, the sensors, the power supply, and microcontrol. Once we have that all grouped together, we go to the final stage, which is completing the robot. And we have 4 general milestones that we were able to complete. They are assembling the robot, goes straight, mapping, and maze solving. Here are the more specific milestones. In our coding section, we have the simulate 6x6, the pulse generator, the ADC, and the simulate 16x16. In our prototyping, we have to print the chassis and the PCB. In the testing section, we have the steps and directions, stopping and turning. In our assembly, we have the final chassis build, and in the final, we have the final speed limit. And in this video here is our mouse solving 6x6.
As we play the video, I'd like to introduce myself. I'm Daniel Cruz, SLA-PUZ, and these people with me, we make up to N.A.V.I. And this was Landy Chan, the man with the man. The man with the plan. We plugged and filled ourselves, and that worked out really well. This was Anthony Ortiz. He told you how we could see those sensors, that ADC. Now there was Justin Mateo. He told you how we go, in case you forgot.
Stepper motors, bro.
Then Bruce Lee, he told you how to get one of these, maybe even 3. Basically, he talked to you about money. And then Victor Nguyen talked to you about our milestones, our ups and downs, but he told you how we're hopeful to win. And now we'd like special thanks to John Kennedy, and Mark Bruno, and all of you, even smaller. We'd like to invite you to our design day where we'll be solving our full 16 by 16 maze. That's May 8th. Thank you.